Hi, so now we've introduced the concept of capacitor. Now we're going to apply that to circuits. So we're going to start with the simplest RC circuit. By RC circuit, what we mean is it's a circuit that contains resistors and capacitors and possibly batteries. But for now, do the simplest one we can think of, which is a circuit that contains only a capacitor and a resistor, and then I have a switch here. Now, I'm going to assume that the capacitor is initially charged. So there are some charges on the place of the capacitor. If the capacitor was uncharged, then nothing will happen here. You have uncharged capacitor, you have a resistor, there's no battery here, you close the switch, nothing will happen. So let's assume that there are some charges that were already put on the capacitor, okay, by some other means that we don't worry about. So someone bring us a capacitor that is charged. There's a little charge here on this plate that I'd call Q initial on the positive plate, and here on the negative plate you'll have minus Q initial. Now, when we close the switch, okay, let me define that. Qi sub I will be the initial charge on the capacitor. So what we'll do now is that we're going to close the switch, and we're going to decide to set t equals 0 when we close the switch. So we start our time or stopwatch at the instant that we close the switch. What will happen? When the capacitor, there were charges here, before we close the switch, when the switch is open, you have charges here, you have positive charges here, they repel one another, but they cannot flow because there cannot be any current in this circuit. If the switch is open, there can be no current, so the charges here are stuck there. As soon as you close the switch, those charges now have a mean to go. Now, you have a lot of positive charges here, so they repel one another. When you close the switch, they will start to flow, and they will flow like this all around the circuit, and they will go here, cancel negative charges. So when you close the switch, you're going to have a large current, but this current will eventually die off. It will, because the charges here, you have many of them flowing out, and eventually they will all have moved out and cancel the negative charges here, and then there will be no current left. So this is very different from if you have a battery. If you have a battery here, you close the switch, you're going to have a current as long as the battery has some energy. But if for a capacitor, you close the switch, the charges will flow out, and very soon, very quickly, the current will go to 0 because all the charges will have moved out of the positive plate. Okay, so let's see what happens when we close the switch in details. So we close the switch, and now then you have currents that will flow in the circuit. Okay, so in what direction? Well, we have positive charges here. Now they have a mean to flow out because you can have a current, so that those charges move to the left. So you're going to end up having a current flowing in this direction, counterclockwise in this case. By the way, this sign here, positive here and negative here, this is not something you can figure out by yourself. You have to be told the way the capacitor is connected. So here let's assume that someone told us this capacitor was connected with its positive plate on the left and the negative plate on the right, and that's given to us. Okay, given that, then we know that when you close the switch, there will be a current this way. If you know that the right direction of the current here, we can assign the polarities to the resistor. This is a positive and negative terminal here. Now that we have the polarities, we can set up an equation. What do we do? Well, here's the key point. The voltage rule that says that the sum of the voltages across along a closed loop is 0. This rule works for any circuit, no matter what's in the circuit. So it should still work here. It works here, even if we have capacitors. So let's do that. Let's say start here, and let's say we go, let's say to go counterclockwise, and I'm going to add all the delta V's around my closed loop. And the sum must be equal to 0. So as I start here, as I go from there to there, there's an increase of potential equal to the voltage across the capacitor that I call delta VC capacitor. So there's an increase of voltage here, and when I go here, there's a drop of voltage, there's a drop of potential, so there's a negative voltage, there's a drop of potential of minus R times I, and the sum must be equal to 0. So we get this. So again, I started here, the potential increases by a value equal to delta V across the capacitor, and then here there's a drop equal to minus R times I. I use a C here to remind us that this delta V is across the capacitor. So this must be equal to 0. Also, notice I make it clear what are the things that vary in time. The current here will change in time. The voltage across the capacitor will change in time because the charges are leaving the capacitor. So we have those functions of time. The resistance R, of course, is a constant. So our goal is to solve this equation, to figure out what's the current, let's say, as a function of time. So this is an equation, but at first, there's not much we can do just with this. Now, remember what delta V across the capacitor is. The basic equation we saw before is that the voltage across the capacitor is equal to the charge on the positive plate divided by the capacitance of the capacitor. So I can replace delta Vc by Qc over the capacitance C. This Q sub C is the charge on the positive plate of the capacitor, okay? So in this equation, this Q is always on the positive plate of the capacitor. So I take this here and I plug for delta Vc. What do I get for an equation? I get this. Okay, now, again, this is not really useful in that form. My goal is to get a differential equation that contains only one function. But now that's not very useful. I have two different functions. I have Q of C, Q on the capacitor as a function of time, and the current as a function of time. I have two different functions. But they're connected, they're related. So my goal is to rewrite this equation in terms of just one function of time. What's the connection? Well, the current we know is connected to a charge. How is it connected? The relationship we saw at the very beginning of the semester is that the current is the derivative of the charge with respect to time. I of t is dq dt. But now there's a subtle point, and I want to emphasize that because the book does not mention it at all, and it's actually very, very important. When we write I of t equal dq dt, the q here is the charge that flows to the wire. Okay, so I call that q sub with a subscript w for the charge in the wire as a function of time. So the current is given by this. Now, the key point is that this charge that flows to the wire is related to the charge on the positive plate, but in a way that is not completely obvious at first. The key relationship is this. The derivative of the charge on the wire, flowing in the wire as a function of time, is equal to minus the derivative of the charge on the capacitor as a function of time. Why the minus sign? The reason is simply this. When you look at dq dt, we're looking at the change with respect to time. When the charge on the positive plate decreases in time, so that way dqc dt is negative, when you decrease the charge on the positive plate, you increase the charge flowing to the wire, right? So a decrease of charge in the positive plate gives you an increase of charges flowing to the wire. That's why there's a minus sign here. When the charge on the positive plate goes down with time, the charge in the wire increases in time because you transfer charges from the positive plate to the wire. So that's the reason for this minus sign here. So what I do now is that I'm going to replace I of t here by dq. Okay, I of t is given by this, but dq dt is equal to minus dqc dt. So in this equation here, we replace I of t by minus dqc dt. And if we do that, we get the following equation. That's the equation we get. Okay, and again, the key point is that this is my I of t. Well, this is minus I of t. So I've replaced here I of t by minus dqc dt, and I get a plus sign here. So that's our equation here. Okay, now we have what we wanted. We have an equation that contains one function and its derivative. And our function is q, the charge on the positive plate as a function of time. I'm going to rewrite things a slightly different way. I'm going to move q over c on the other side, divide both sides by r, and I get the following equation. Okay, so all I did is that I isolated dqc dt equal, and that's minus q over rc. Okay, that's our differential equation. We know now to solve that r and c are constants, right? They're not functions of time. So you're looking for a function of time that when you take its derivative, you get back the same function multiplied by minus 1 over rc. So you can guess the answer. We're going to work it out now, but you can guess the answer. You expect to have an exponential. But let's work it out. Let's say we didn't see the answer. What we do is that we use a trick I've mentioned in class. To solve this, I'm going to move, so there are two R and C are constant. There are two variables. There's a Q here and a Q here. Well, dq and Q on the other side, and then you have dt. So I move dt on that side, and then move this Q on the other side. So I get this. I get dq over Q is equal to minus dt over RC. So I've isolated everything that depends on Q on one side, and everything that depends on the time on the other side. The R and the C and the minus sign here, I could have left on this side here. I could have minus RC here. It doesn't make any difference. But I put everything that depends on the variable Q on one side and everything that depends on the time on the other side. And then once I have that, I integrate both sides. So the integral of this, again, think of Q as let's say like y of x, right? So this is like your y, Q is like y, and t is like x. So I get this here, and now I integrate this. Okay, forget this function of time here. You have dq over q. What's the integral of that? It's ln of q. The integral of dt is just t. So we integrate, and we get ln of q plus a constant of integration is equal to minus, the integral of dt is t. So you get minus t over rc plus a second constant of integration. For the constant of integration, I use k instead of c because we already use c for capacitance here. So I use k, k1, k2. And that's it. All we have to do is that we have to solve for q as a function of time. So the first thing to do is to move the plus q, k1 here, which is any constant on the other side, and then we'll take the exponential of both sides. So let me write the equation. I've moved the k1 on this side, so I have k2 minus k1. Now to get q of t, I just raised, no, I take e to the left side equal e to the right side. So we get qc is equal e to the minus t over rc multiplied by e to the k2 minus k1. Okay, so that's it. That's q as a function of time. Now e to the k2 minus k1, k2 and k1 are some arbitrary constant, and e to the some constant is just another constant. So we'll just rename that here. We call this combination here, we just call that capital K. Okay, that's what I rename K here. And that's it. That's our charge on the positive plate of the capacitor as a function of time. Now this constant here for now can be anything, but there's a way to fix it. To fix it, we have to use what we call an initial condition. Okay, remember that, okay, that's our solution, but remember that we know one value of Q at one specific time. When we closed the switch, we knew that the charge was equal to Q sub I. That's some value that would have been given to us in the problem. So to fix K, we impose that at t equals 0, the charge on the capacitor is equal to this Qi, which is some number that someone should have given us. So now we're going to impose that. I'm going to set that. So I impose that equation. So I impose this here. This Q at t equals 0 equal to Qi. So go back here. Okay, look at this equation here. Qc at t equals 0 is this thing here evaluated at t equals 0. So I set t equals 0 here. What do I get? I get e to the minus 0 over Rc, which is just e to the 0. So Q at t equals 0 is just k times e to the 0. And I say this must be equal to Q sub I. That's it. Now e to the 0 is equal to what? You should know that any number raised to the power 0 is equal to 1, right? So e to the 0, that's just 1 here. So you have that k is equal to Qi. K is equal to Qi. So now I go back here, and I know k is equal to Qi, and I can write, finally, this is the solution. This is the charge on the positive plate as a function of time for a discharging capacitor. We call that the discharging capacitor because it's discharging, obviously. Once you know discharge here, the charge as a function of time, you can calculate anything you want. You can calculate voltages everywhere. You can calculate the current. You can calculate any information, energy, anything you want. We'll see that later. But our goal was to get this equation, and that's it. That's our result. Okay. Just a little comment. If you go back, you look at the units. Remember that we have, if you look at the basic units from Ohm's law, delta V equal Ri. So 1 ohm is 1 volt per ampere. That's one way to write 1 ohm. From the equation for the capacitors, we know that the capacitance is the charge divided by the voltage on the capacitor. So you see, that's in farad, capacitance in farad. So you see from this equation that 1 farad is equal to 1 coulomb over 1 volt. Now, look at this. In the exponential, we have R times C. The product R times C is in okay, this should be okay. So R times C is equal to a resistance multiplied by a capacitance. If you multiply this by this, you see the volts cancel out, and you're left with coulombs per ampere. But 1 ampere is 1 coulomb per second, so RC is in coulombs per second. The coulombs cancel out, and you're left with seconds. So RC, this number here, is actually something in seconds. If you give the resistance in ohms and you give the capacitance in farad, you must go back to farad and ohms. Then R times C will give you a time in seconds. So actually, the product R times C is a number that depends on the resistance and the capacitance you have in your circuit, but it's a number in seconds. We give that a special name, this product. We call that the time constant of the circuit. And we use tau again. I know it's confusing. We've used before tau to be the average time between collisions in a wire, but in those circuits, when you have capacitors, the tau we're going to use always means the product of R times C, and it's a time in seconds. Okay, and we'll call that the time constant of our circuit. So finally, using this notation, if you have a capacitor that you discharge, so you have a capacitor that has some charge initially, you close the switch and it starts to discharge. The charge on the positive plate as a function of time is given by the initial charge multiplied by e to the minus t over tau, where tau is R times C. And what it tells us that you have a graph like this. If you look at the charge as a function of time, it follows a decreasing exponential. We're going to do calculation in class, but so this is, let's say you have, it's fully charged at t equals 0, and as a function of time, it will drop, and later, for example, we'll find that when you wait a time equal to RC, one time constant, the charge will have dropped to 37% of the initial charge, and then we'll do other calculations later on. But the key point is that the charge on the plate of the capacitor, you knew it was going down, but what exactly, how does it go down as a function of time? It follows a decreasing exponential. Okay, and we'll do examples in class of calculations using that. Thank you.